what if we can't calculate the integral to find the area between the x-axis and a function? Is there a way we can approximate it? And we can. We can using, what we know about areas. So for example, this is the function of x squared, right? So this is y equals x squared. And we're asked to approximate the integral between 1 and 3, right? So we want to know basically what the area is between here and here, right? So in other words, this area down below the curve, right? Between the curve and the x-axis. So there are lots of different ways to do this, and we're going to go through a few of them today. But the first one is, can we do this with rectangles of equal width with left-hand endpoints? That might sound complicated, but what we can do is we can essentially approximate this area using a bunch of rectangles. So I'm just going to arbitrarily choose 4 rectangles. I just think it fits nicely. So we'll make one rectangle. Hold on. We'll make one rectangle like this, one rectangle like this, one rectangle like this, and one rectangle like this. So the width of each of the rectangles, or in other words, delta x, in this case, is going to be 0.5. And again, this is arbitrary. I just chose to break this up into 4. I could have broken it up into 8. I could have broken it up into 2. But 4 is a good number. So now the question is, what is the height of each of those rectangles? And this one says rectangles with equal width with left-hand endpoints. And what that specifically means is it means we look at the left side of each of these rectangles, and that's where we sort of cut off the rectangle. So I'm going to go up here. This rectangle is going to get cut off right here. This rectangle is going to get cut off right here. Basically when the left side of the rectangle touches f of x, or the function, right? So that's it. Can we now approximate the area under the curve just by finding the area of these 4 rectangles, right? And that's what we're going to do. So what this looks like, the area of each rectangle, length times width, right? So one way we're going to do area is approximately equal to, well, length times width. So for the first one, we have the width is delta x, we know that, and the height is going to be the function evaluated at 1, right? Because this is 1, this is a value of 1. I know I sort of covered it up there, but this is a value of 1. So it's going to be whatever f at 1 is times delta x. The second rectangle is going to be f at 1.5, right? If this is 1.5, this is 1. It's going to be f at 1.5 times delta x. The next one is going to be the function at 2, right? Delta x. And the last one's going to be the function at 2.5. Delta x. Notice how we don't actually need what the function is at 3 because the rectangle, we're only using the left side of the rectangle. So I can just calculate this, but before calculating it, you might realize that we can actually simplify this a little bit, right? We can factor out a delta x, so we don't have to actually multiply each one like that. We can simplify it so it's delta x, because the delta x is the same for all of them, right? And this is just going to be f at 1 plus f at 1.5 plus f at 2 plus f at 2.5, right? So if we were to actually calculate this, we could do delta x is 0.5, f at 1, well, x squared at 1 is just 1, 1.5, the value 1.5, well, if we do 1.5 squared, what does that give us? 1.5 squared is 2.25, right? Or as a fraction, 9 over 4. Plus f at 2, which is 4, right? 2 squared is 4, plus f at 2.5. So 2.5 squared, that's 6.25, or 25 over 4. I'm just putting the fractions so we can find sort of the exact answer. And then we know the 0.5 is also 1/2. But anyways, we can sort of just add these up. 25 over 4 plus 9 over 4 plus 1 times 0.5 is 6.75. So the total area is 6.75. Okay, so that's one way to approximate the area of the integral, right? Or to evaluate the integral, or to find the area below the curve, right? Is to do that. We can do the same thing, however, with right-hand endpoints. So realize here we did the left hand, we made the rectangle go up to the left side. We can do the same thing here with the right side. So in this case, our rectangles we'll do the same. We'll do the same width, just so we can compare. Again, usually in a question, you'll be told how many segments to break it up into. But in this case, we're going to make the rectangles go up to the left side. So here, the function goes up to the left side. So that's the rectangle we're going to make. Here it goes right here. So we evaluated at 2, at 2.5, and at 3. So notice this time, we don't actually care about what the function is at 1, right? We didn't use this y-coordinate. But anyways, we could do the same thing, right? So now we know the area, we can approximate it with delta x, so f at 1, sorry, not 1, 1.5, 2, 2.5, and 3, right? So we can do f at 1.5 delta x plus f at 2 delta x, right? Because we always need to multiply by the width, and we'll call the width delta x, plus f at 2.5 delta x plus f at 3 delta x. And again, I'm going to factor out the delta x just to make it easier. So essentially, we're just adding up these. F at 2 plus f at 2.5 plus f at 3. Right? And again, you can calculate that. And if you do, you end up getting 10.75. You can trust me, you can calculate it yourself, whatever you want. Okay, so that was this area essentially that we calculated, right? These 4 rectangles. Now my question to you is, what do you notice about those 2 numbers? One of them is much higher than the other, right? Which one's better? Which one's a better estimate of the area? Well, let's do that. Why don't we just evaluate this integral? Why don't we see what the exact answer is, right? So to find the exact answer, to integrate that, what we're going to do, we just integrate x squared, right? So the integral of x squared is 1/3 x cubed. And we have to evaluate that between 1 and 3, right? Evaluate at 3, evaluate at 1, and subtract. So we have 1/3 times 3 cubed minus 1/3 times 1 cubed. So that is, I believe that's 9 minus 1/3, which comes out to 26/3. Or as a decimal, if I change it to a decimal, it's 8.66 repeating, right? So we'll just round it like that. It's approximately 8.67. So that's the exact answer. Now we can calculate that because this is an easy one, but it won't always be this easy to calculate, which is why we have to approximate sometimes. But anyways, which one's closer? Well, you can see obviously that this is between these 2 answers, which makes sense if we think about it, because this one is always going to be underestimating because it's leaving out these rectangle or these triangle-like shapes here, right? They're not actually triangles because these are actually curves. They're not straight lines. So we know that this is going to be an underestimate, right, in this case. And we know that this one, it includes this extra area because the area we're trying to find, if I switch back to blue here, the area we were trying to find was this area down here, right? The area between the function and the axis. So these areas up here are extra areas. So this is going to be an overestimate, right? So can we come up with one that's going to be better? Well, these 2 are pretty simple, which is why we use them a lot of the time. They're the easiest ones. But we can get a little bit more creative. We can, instead of picking the left side or the right side for the height of the rectangle, why don't we use the midpoint, right? So let's do those same 4 triangles, right? Or rectangles, sorry. So I'm dividing up my width into 4, same as last time. So my delta x is still 0.5, right? But what I'm going to do, instead of making the rectangle go up to the left or the right, I'm going to go up to the middle. So if we look at the middle of each rectangle, that's the height. So that goes to the function. So we're going to pick that point. And here we have this one, right? That goes up to the middle. And this one goes up to the middle. And this one goes up to the middle. Right? Now that looks like a better estimation, right? Because it's got some extra area here and it's missing some area here. So I think, maybe this is a better estimation. Now the problem with this is a little bit trickier because the midpoints, we have to evaluate it, right? At these midpoints. So if this is 1.5 here, we have to realize that these midpoints are going to happen in between. So this is going to be actually at 1.25. And this is going to be at 1.75. And this is going to be at 2.25. And this is going to be at 2.75. So just it's a little more complicated to figure out where those midpoints are. But, it's not too bad. So what I want you to do, I want you to try to evaluate this one yourself. See if you can come up with the approximate area. Pause the video here, try it yourself. I got 8.625, which if we go back, that's very close because our actual answer is 8.66667, right? So that's actually very close. It's a much better estimate, right? A little bit more difficult to find, but a much better estimate. So that's another way we can approximate it, which may be more accurate. And then lastly, we have trapezoids of equal width. So we're going to divide up, because it says equal width, we're going to divide up to the same 4 things, right? Same 4 rectangles. So the width is still going to be 0.5. Delta x is 0.5 for all of these. Now, what it means by a trapezoid is it means we actually go up on the left side and the right side. And what we do is we join those two with a line. So it's a trapezoid. So these are funny trapezoids. They're not your regular trapezoids that you're used to seeing looking like this, right? They're a little bit more, they're a little bit different because the bottoms are all flat, but they're still trapezoids, right? And then this one like this. So now we have 4 trapezoids. And do you remember how to find the area of a trapezoid? Well, if this is your trapezoid up here, let's call this A and let's call this B and let's call this the height of the trapezoid. Usually it would be, which you maybe learned in grade 9 or grade 8 or grade 7 or grade 6, the area of a trapezoid is the average of the 2 parallel sides times the height, right? So it's basically A plus B over 2 times the height, right? That's what it is. That's the area of a trapezoid. That's the area of a trapezoid. So in this case, it's the same thing, right? The average of the 2 parallel sides, so the average of this side and this side, for example, times the height. Well, in this case, the height is actually the width here, which is 0.5. But we need to essentially find the average of this and this. So we can write that as A is approximately equal to, so for our first one, so we're gonna do it at 1 and 1.5. Take the average of f at 1 and 1.5, right? So it's going to be f at 1 plus f at 1.5 all over 2 to find the average of them times delta x, right? And then for the second rectangle, or the second trapezoid, I should say, it's going to be f at 1.5, right, this width, plus this height, right, over 2 to find the average of those two, plus f at 2 over 2 times delta x. And we can continue that for the rest of them. I'm going to run off the page here. F at 2 plus f at 2.5 all over 2 times delta x. And the last one plus f at 2.5 plus f at 3 all over 2 delta x. So that one, obviously, this one's a little bit more complicated, right? But let's see what happens when we simplify it. So if we simplify this one, we can sort of pull some stuff out, right? We can pull the x out, we can factor out the x, but we can also factor out the 2. So if you realize we can simplify this, it gets a lot easier. So we're going to factor out the delta x over 2, basically, right? And what are we left with when we factor those out of each terms? Well, there's f at 1 plus f at 1.5. That's from the first term. From the second term, we have f at 1.5 plus f at 2 plus f at 2 plus f at 2.5 plus f at 2.5, oops, plus f at 3, right? Now you might see a little bit of a pattern here. Do you see how like this is used twice, 1.5 is used twice, 2 is used twice, 2.5 is used twice? And this is always going to happen with the trapezoidal ones because this, for example, is used by this trapezoid as well as this trapezoid, right? So we can actually further simplify this, and this is a pattern. It can really help to simplify the calculations if you realize this or if you remember this for the trapezoidal rule. It's f at 1 plus 2 f at 1.5 plus 2 f at 2 plus 2 f at 2.5 plus f at 3. So the outside ones are only used once, right? 1 and 3 are only used once, but all the in-between ones are just used twice. So if you remember that pattern, you could just use this as sort of your pattern instead of this. But it always helps to write this out to see where that pattern comes from. So anyways, I'm going to pause the video here, or you should pause the video here. See if you can calculate this yourself and see what you get. And if you do that, you should get, I believe, 8.75, which if we look again at our answer, the midpoint one was actually closer, right? This isn't always going to be the case, but just for this case, it was, okay? So these methods are just different methods, and the question might say use one or use the other, but you just got to sort of know how to do all of them. So remember, it just comes down to where you pick the endpoints, and the trapezoidal one is just a little more complicated because you need to use, you need to find the average of the heights, okay? What I want you to do now is I actually want you to try the 3 examples on the next page. So there's the first one, approximate e to the x from 0 to 2 using 4 right-hand rectangles. Pi or sine x from pi by 4 to pi using 4 trapezoids. And lastly, the area between the x-axis and the graph defined by points. So these are defined by points instead of a function. So you're just going to have to use those points. So pause the video here, try those 3 problems yourself. I actually just want to make one change. Let's make this, for example, 3. Let's make 3 trapezoids. Just because the interval delta x comes out to something funny if you use 4 trapezoids. Much easier if you use 3 trapezoids. Okay? So give these a shot and unpause the video when you have an answer. So let's have a look at these solutions now. So first of all, if we find the exact area between this exponential and the axis, it comes to 6.389. Using our right endpoints, the value comes out higher. And that makes sense because, we've got this overestimation of area, right? There's those little pieces of the rectangle that are always going to be bigger than the graph, so it makes sense that it's a bigger value. Notice how the delta x in this case was 0.5. The second one, the actual answer, the actual integral between pi by 4 and pi of sine x is 1.707. And using the trapezoidal rule, by the way, notice the last one isn't really a trapezoid at all, right? Realize it's a triangle, but a triangle you can think of as like a trapezoid where one of the sides is 0, right? So it still follows the same rule. It's just that this value over here is going to be 0, which is fine. So we're basically just finding, for the first part of sine here, the area between pi by 4 and pi. And notice how a sketch sometimes helps you figure out what those delta x's are. But if you're stuck on how to find out what the width of that delta x is, remember you can do like the final minus the initial divided by the number of segments, right? Because you want to find the difference between them and divide it up. So if you wanted to use that, you could do pi minus pi by 4 divided by 3 to find out what the delta x is. So in this case, the delta x is pi by 4, which again, you could figure out just by sketching it. When you apply your trapezoidal rule, I did the simplified one, right, where the middle terms are doubled. I ended up getting this expression down here, the exact answer, but then I just evaluated to the decimal so we can compare it to this, which it's pretty close, right? It is an underestimate, which makes sense for the trapezoidal rule in this case because, here we can see that, this triangle is an underestimate, for example, of this, and all the other ones actually will be an underestimate as well. you can think about when a trapezoidal rule will be an underestimate, when it will be an overestimate. There's, it's an interesting little thought experiment there. And then lastly, there's this one. And this one is a little bit different because it doesn't give you an equation. It just gives you some data. And the other difference is that the x values that I gave you are 1, 2, 3, and 10. Notice how they're not evenly spaced apart. So if you were to sketch it, you can see that, like, what I would do is I would sketch it and plot those points roughly. You can see that those delta x's are not going to be the same. But that's okay. We can still use delta x's that are not equal to find an area, to approximate an area. And in order to do that, I labeled delta x1, delta x2, and delta x3. Delta x1 and delta x2 were both 1 unit wide, but delta x3 was 7 units wide. So when we're finding the area, we just got to be careful about that. We can't factor out the delta x because they're all different. So anyways, when you find the area, it ends up being 49. All right, there we go.